Okay guys, here's our last section of Unit 7. So we're going to do 5.3, talk about the fundamental theorem of calculus. In 4.9, we started discussing antiderivatives or indefinite integrals, where we were finding the antiderivative, the previous function, given a derivative, right? In 5.1, we discussed estimating the area underneath the curve by using rectangles, finding the antiderivative by estimating using Riemann sums, so rectangles. And in 5.2, we talked about finding the exact area underneath the curve, either the long way, which we skipped, doing an infinite number of rectangles, or we can find the exact area if we know exact geometric shapes, and we can use those to find the area. Well, now in 5.3, we're going to find the exact area underneath the curve. We're going to find the definite integral. We're going to find the antiderivative from a to b using fundamental theorem of calculus. There's actually two pieces to the fundamental theorem of calculus. We'll talk about one of them now, and then we'll talk about the second one later in this section. So the fundamental theorem of calculus says that if f is continuous on the interval from a to b, and big F, capital F, is the antiderivative, well then when I go to integrate little f, I end up getting big F, and I'm finding its value from a to b. So I'm finding the value of the antiderivative over the interval from a to b. So for example, if this were a velocity and I was asking you to integrate it from 1 to 3, what you're really finding is the position from 1 to 3. Okay, finding the antiderivative value from a to b. Let's do a few problems. I will show you how you do not need a plus c. We only need a plus c when we're doing an indefinite integral. And so if I ask you to integrate f of x, what you're finding is a function that represents the antiderivative, and there could be any constant of integration back there. But when you're doing a definite integral, you're finding the area underneath the curve. What you're getting is an actual value for the area. And so you don't get a function with a constant of integration, a plus c. You actually get a number when we're using the fundamental theorem of calculus. Let's do a few examples. As we go through, they'll get a little more complicated. If you look at example number 1, it asks us to evaluate the integral of x cubed from 1 to 3. Find me the exact area underneath the curve of an x cubed graph from 1 to 3. Without using Riemann sums, without using shapes, can we find the antiderivative of x cubed from 1 to 3? Well, using our antiderivative or integration rules, you should be able to use your power rule and integrate that for me. You should get an x to the 4th over 4. And then we're going to evaluate that from 1 to 3. And so some books use like that straight line. Some books use like a little bracket to represent that we're evaluating this function from 1 to 3. You notice that I didn't add a plus c because we're doing a definite integral. We should be getting just a number as our final answer. What I'm going to do now is I'm going to figure out what the value is of this at my endpoints, so my upper limit, minus my lower limit. So I'm going to try to find the value from 1 to 3. So you find the value at 3, you find the value at 1, and you subtract them. So I plugged in my upper limit, my 3. I plugged in my lower limit, my 1. I ended up getting 81 over 4 minus 1 over 4, or 80 over 4. And so that means the area underneath this curve of x cubed from 1 to 3 is 20. Another interpretation is the value of my antiderivative from 1 to 3 is also 20. Okay, and that's the exact area, not using rectangles, not using shapes, but by using our fundamental theorem of calculus. So look at part B with me. It asks us to integrate x squared minus 3 from 1 to 2. And so I can take this and I can integrate it. I have my power rule of x cubed over 3 minus 3x, and I'm going to evaluate it from 1 to 2. That means I'm going to plug in my upper limit always, my 2 first. Then I'm going to plug in my 1. And then I'm going to find the change in there, the difference, subtract them. I ended up getting negative 2 over 3. Now this looks a little bit different than the first example. Do you see how it's negative? Do you remember what that negative means? Yeah, it just means that more of your area is below the x-axis than above. It doesn't necessarily mean that all of it is, it just means that more of it is below than above, and that's why the answer turns out to be negative. Okay, let's do a few more in this video. If you look at example C, it asks us to integrate 3 times the square root of x from 1 to 4. I had a red flag, I don't know about you, and so I rewrote this as the integral of 3x to the 1/2 from 1 to 4. I was then able to use my power rule, my rules for integration, add 1 to the exponent, divide by that new exponent, or multiply by his reciprocal, and then I can evaluate it from 4 to 1. Plugging in your upper limit first always, plugging in your lower limit next, and then finding the difference. And instead of evaluating 4 to the 3/2 power, I converted that back into radicals. Remember, top dog goes in the house, so I have a 3 on the inside underneath a square root. You could do either order. I ended up doing the square root of 4 first, which was 2, and then cubing it, and then multiplying it by 2. I ended up getting 16. I took the square root of 1, which is 1, then I cubed it, and then I multiplied it by 2 and got 2. And so I can tell you that the area underneath the curve from 1 to 4 is 14. The value of my antiderivative from 1 to 4 is 14. All right, let's do another one, and then we'll do another video for the other examples. Here's a little bit of trig. So I want to evaluate secant squared from 0 to pi over 4. And so is there an antiderivative for secant squared? What function has a derivative of secant squared? Well, hopefully you've been practicing your integration rules. Hopefully you've printed off that quiz. You've taken it a few times to make sure you know all the rules. But the antiderivative of secant squared is tangent. So we can evaluate tangent x from 0 to pi over 4. Plugging in our pi over 4, plugging in our 0, and then using our unit circle. So hopefully you remember your unit circle also. Tangent at pi over 4 is 1. Tangent of 0 at 0 is 0, and so 1 minus 0, you should get an exact value of 1. All right, using our fundamental theorem of calculus to find the exact area underneath the curve. We'll do some more examples in the next video. I hope you guys are doing well. Let me know if you have questions.